Hi, everyone. Welcome to the SAEM Research Learning Series course online lecture titled Deep Learning. As we begin today, please write down and save any questions you may have for the end of the presentation. Please use the chat box at the bottom of your screen. You can enter your questions there during the Q&A portion of the lecture. This presentation is being recorded and will be available shortly following today's session. And now it is my pleasure to introduce to you Dr. Richard Andrew Taylor. Dr. Taylor is an associate professor of emergency medicine at the Yale School of Medicine. Dr. Taylor, I will now turn it over to you.
Thanks, John. And thanks everybody for joining today. So we're going to talk about probably a subject or an area that a lot of people aren't too familiar with, or may have heard a lot within the lay press and other areas, but may not have necessarily applied it to their own research. And so my hope is today is to kind of take away some pointers and just to get to some general level of understanding about kind of what deep learning is and how it might be helpful for emergency medicine. Both from a practical standpoint and also from a research standpoint. So I think, John, you covered it nicely kind of about myself, so I will skip this slide at this point. These are the disclosures that I have currently. And so we'll cover these objectives. So first, I wanted to just give you kind of a motivation or try to get some type of understanding for why deep learning has kind of gained that press that it's being shown in the media, and then also to kind of understand how that translates into the medical space. And then I wanted to cover some just basic aspects of deep learning. I will try to avoid all math as possible. I checked there's only one or two equations in this whole lecture, so please bear with me through that part. But I wanted to give more of a conceptual understanding than an actual kind of heavy math-based presentation. And then I want to walk through several different types of applications of deep learning, and then kind of at the end of that kind of cover some of the things that you might look forward in your own research and some of the potential limitations of deep learning currently. So I think the big question is why should you care about deep learning? What does it have to do with emergency medicine? And really the main issue for me is a performance. So I take it and kind of look at it from this perspective. I used to have a 1996 Nissan Maxima. And I think, currently now, if you looked at the kind of space of prediction and trying to make classifications for various things, you could kind of say that my Nissan Maxima was kind of the logistic regression of the past. And then my son is fixated on a car that's way too expensive, but it's a Bugatti. And I think deep learning is kind of in that space. Now, there's not that much true difference in the percentage of kind of prediction errors between those two. And you'll see some examples of kind of where there are differences, but it's enough to, I think, push things forward. And it was enough of a change over the last 8 to 10 years to really move deep learning into the kind of state-of-the-art space. And so the other question you might have is then, so why are there performance differences? So what's so different or what's so unique about deep learning? And one of the main things I wanted you to kind of take away today was this idea behind that learning algorithms generally depend on data representation. And deep learning really is a method to better represent data and then use that data representation for different tasks, so for classifications and regressions, and we'll talk about that briefly. And so what are some of the areas that need better data representation, or some of the areas that we're often confronted with medical data? So one thing I think we always kind of think about, even when you're building like a logistic regression model or something like that, is you think about variable interactions. So how is blood pressure interacting with heart rate, and if I'm trying to predict something like sepsis, and do I need to come up with some type of kind of preconceived formula behind that, or some type of representation of that interaction, and put that into the model itself? Can I build in components into the model that would kind of account for those interactions? The other thing that I think don't often kind of handle when we're building models or making predictions or really thinking about kind of things like that is temporal aspect of data, but it's a big component of kind of what we do and how we make decisions. So leveraging, prior information about the patient, prior visit information, prior medications that they were given, even, prior vital signs and everything else. And it's hard to represent that data in a temporal kind of fashion well without using some type of deep learning technique. Another area, and I think the real start for where deep learning kind of took off, was in the spatial representation. I think most of the time in the medical kind of domain or field, we think about this from diagnostic imaging, and I'm sure that many of you are kind of aware of some of the newer kind of AI or deep learning techniques that are being used in radiology. We'll talk a little bit about that moving forward and kind of why that's the case. But that was where really I think some of the initial kind of major breakthroughs were happening around in the early 2010, 2012 time period, and really kind of pushed deep learning forward. And we'll talk a little bit about that. The other kind of space, and I think there's been a lot of development over the last probably 3 to 4 years in this area, is in natural language processing, and really getting to some type of kind of contextual representation of data. So, I have some word in a sentence, and it's surrounded by other words in the sentence, and what does that mean for that word? And the changing representation of that word depending on what's kind of surrounding it. And then lastly, a newer area that's cropping up, and I think it's been kind of a really hot area, is the use of graph data, or graph representations of data. I think there's some unique aspects about graph. There's a movement towards incorporating knowledge graphs, or kind of graphs of information that can be stored, and text and other things, and changing kind of the relationships between that information, or representing that in a different way. And we'll talk about deep learning and how it kind of works within that space as well. So I wanted, just to kind of start out with some of the basics of deep learning, recognizing that most people aren't going to have kind of the math background to really kind of get heavy into that space, but I wanted to present more of kind of a conceptual basis for thinking about deep learning. And really the kind of purpose of all machine learning, and deep learning in particular, is that you have some data that you're confronted with, and you have a model that you're using, and then you have some objective that you kind of would like to get out of that data. I think sepsis is a nice example, but there's plenty of others. So it could be, identifying intracranial hemorrhages in CT scans. So there's a lot of potential applications, and the idea is that you use the data to kind of learn that particular objective, and so that there's this kind of teaching process and manipulation or changing of the function through kind of feeding it data and examples of kind of what would be kind of positive or negative examples within the objective itself. And so I kind of wanted to give just a very basic example of kind of the network architecture, but then also to kind of hopefully bring this back to what many of you are probably familiar with, which is more kind of on the logistic regression side of things. So you can kind of think of it, would be like a very, very basic neural network that has 2 inputs. So an input for heart rate, an input for systolic blood pressure, and an output is trying to determine whether a patient has sepsis. And then you have have weights that kind of weigh the relative input from heart rate and the systolic blood pressure, which are represented by beta 1 and beta 2 here, that kind of to say, how much of the heart rate will be kind of a function for the output and how much of the systolic blood pressure. Because it's a categorical, you may have kind of heard of a logistic function or a sigmoid function. That's what this sigmoid sign here is. But you get this basic equation that comes out of this. And this looks, very much like what you're probably used to with like linear regression or logistic regression, where you have some coefficients, you have your variables, and you're trying to kind of learn those coefficients. In neural networks, they're called weights, but the basics are the same. So that's kind of where you start with this. And you'll notice that there's a few things that kind of happen with this to begin with. Is that one, it's hard if there's some dependency on the outcome of sepsis to be quadratic or some other particular nonlinear form. It's going to be very hard, and for this particular network, it would be impossible to kind of learn that representation. And so what the neural networks kind of the deep learning aspect of things does is it changes that, or it kind of creates this additional layer or series of layers that are really there to change the representation of the data. And I'll go through this a little bit. So the idea is that we have this, instead of just the input layer and output layer, we have this hidden layer that's in the middle. And in modern deep learning networks, these hidden layers can be hundreds of layers deep. You can have, and the nodes within the individual layers can be in the thousands or millions. So they can be very, very wide and very deep. But just for simplicity's sake, I just included just one hidden layer here. And the idea is that you have these three hidden nodes within the network, and you have your input variables, and they feed into these hidden nodes that are underlying the model itself. And what those hidden nodes allow you to be able to do is to combine the initial input layers that you have into new features or new representations of the data. And so that now, instead of just having heart rate, your final kind of sepsis outcome being a function of just a linear function of just heart rate and just systolic blood pressure, it now becomes some type of combination where you can combine heart rate and systolic blood pressure into some kind of representation, and that would be represented by A. You can take another kind of combination of those two variables, and that can be represented by B. And you can take another combination of those two variables, and that would be represented by C. And then those kind of really become your new data representation for the model, and then you make a prediction, a final prediction off of that. And so this is just kind of showing that in an equation form on the right-hand side, and you can see that this now what you would traditionally kind of consider your variable has taken a form where it's some combination of your heart rate and systolic blood pressure. And so this gets to that idea of like modeling in interactions or modeling in kind of spatial considerations. And we'll go through kind of the differences in the different kind of data applications that you might have. But that's what the network is doing, is kind of learning that data, underlying data representation. And I'll kind of show two examples from this. And the one we talked about, kind of the linearity of the potential kind of outcome and where you may be constrained. So if you're only able to learn a linear representation, if this is kind of your data set and you're trying to fit it, you're obviously not going to be able to kind of get to a good fit. But if you have the ability or flexibility within the modeling structure to be able to kind of change things and learn complex dependencies between the variables, you can get to a much better kind of representation of this. I think this is a better kind of example. And so what this is showing is a classification task, and you have two basically classes that you're trying to predict. They start out in this very kind of complex relationship, and I'll start that just back again so you can see it. And where you can't really linearly separate the data out. What this is showing is that as the model is kind of learning a new representation of data, it starts to stretch and change the way that that data is represented. And then it gets to some particular kind of representation where you can easily separate out the data based on linear, just kind of linear final model within the thing. And I guess one other thing I wanted to say about this was that the final kind of top of the model for a lot of these deep learning structures is really just a logistic regression, or kind of a support, what would be considered kind of like a support vector machine on top. So the idea is that you want to kind of change or massage or manipulate the data representation kind of internally within the neural network itself until you can get to a point where you can easily linearly separate the data. And then that's when the final kind of prediction or classification is made. And so that's the general idea behind this. I talked a little bit about kind of the historical aspect of things. So I really wanted to just to highlight, I think most people would say back in 2012, there was a paper that came out that significantly improved classification for images. And really that, I think, was the kind of major start of kind of the deep learning boom. But you can see there's been a lot of work on deep learning that's been going on for a long time. It's not really a new concept. A lot of these kind of developments that were in the past were really hindered by just the computational constraints and kind of what we had from a computer architecture at that point. And so those were some of the major limiting things about why we didn't see deep learning kind of moving more quickly in the 80s and 90s. So there's several different kind of domains that I wanted to talk about, and I think that have applications to kind of emergency medicines. We're going to cover each of these, and we're going to cover kind of imaging or diagnostic imaging, text data that you may see, tables or tabular data, and then some graph-based data. I'm going to go through each of these. So we're going to cover first when deep learning for imaging data. This can be several different things. It could be EKG reports. We talked a little bit about CT scans and kind of identification of bleeding on CT scans. There's also been a lot of work around identification of pneumonia on chest X-rays, and all of these things have seen, I think, significant improvements over the last couple of years, with some reported papers being as good or having comparative results to radiology interpretations. And so kind of what's the idea behind this, and kind of why does it work well, and why might have previous kind of efforts to do types of classification tasks and other things on this type of data that have not worked well. And so you can kind of see this is a general kind of presentation of the data and how it's represented when it comes to imaging, and you usually get some type of scale. It's going to be 1 or 0 to 255, which is kind of your full kind of spectrum of the differences in the grayscale that you might see. And then you can think of all these numbers on the kind of far right, or kind of the differences between blacks and whites on the screen is representative numbers, and those are your features that eventually go into making some type of prediction. And a lot of the initial work around this was in kind of handcrafting features to figure out, I need to detect a boundary here. We want to be able to detect circles. We want to be able to kind of separate two things out very well. And so there was a lot of work, but what people were doing at the time was they were handcrafting, kind of building up equations that could handle that type of information or identify those types of features. And what's different about deep learning is that there's not really that kind of handcrafted nature to the feature or the feature engineering. It's all automated and kind of sits within that kind of middle part, those hidden layers within the network architecture. And what that's done is it's accelerated kind of the feature detection. It's made it possible to really kind of scale out and really kind of move forward in this space. And so what people have done, and this is kind of the idea, and this was the kind of major network architecture that's used for imaging data. It's called convolutional neural nets. Basically, you can kind of think of it as there are a series of kind of intermediate or hidden nodes within the network that look at small regions of the image itself and basically are trying to identify those types of features that we may be interested in. So, differences in color, differences in kind of slants or kind of borders within the data, and then they're gradually construct up to kind of more higher level features within the data. And I'll show kind of you what that looks like on a more complicated neural network architecture. So I'll just kind of walk you through this on the top part here. So basically, this is kind of the initial image that you have through that's being put through the neural network. Then you have a series of what are called convolutional kind of aspects of the network. There's different pooling parts, which means you're kind of averaging those small little segments together, and that can be shown to have several different advantages for these types of things. But the basic idea is you have this kind of, have these multiple hidden layers that are on the inside of the neural network that are learning, continually kind of updating and learning different hierarchical kind of features within the image itself. So kind of within the first layer, it might start learning things that have color representations that have different slants to the data and different kind of edge detectors. And then it starts to kind of in the third layer, after it's combined some of these initial features together, you start noticing different types of textures. And then you can get to a part where you start noticing different types of object parts. And then finally, you get to this kind of very abstract, high kind of level representation of the data, and you finally make your prediction off of that. And so in the past, all of these things would have had to have been handcrafted in some way. And you can see how it would be extremely difficult. It's hard to know where even to start to say, how do I identify, or how do I craft a feature to identify like a puppy nose? But what's really nice about the deep learning aspect is that it learns all of these features inherently within its structure. So one of the kind of applications that we've looked at recently is combining some mimic data and looking at pre-labeled data for pneumonias, and then identifying kind of areas within the chest x-rays that would be representative or have a higher likelihood of having pneumonia. So you can see this is a deep learning architecture that kind of identifies areas that would be suggestive of pneumonia within the chest x-ray itself. And also, I saw that there's several people on. If you have any questions or anything else, feel free to just send a text through the chat. I'm happy to answer those as we move along as well. So the next area I wanted to kind of cover was deep learning for text data. I covered a little bit about this within the prior lecture that I did on natural language processing, but I wanted to kind of really focus on just the deep learning aspect of things. And I think this is kind of a good example, and I'll let you read it. I won't read out these two things, but I think this is a good example of kind of how much information can be conveyed in text, and how different that information can be based on its context, kind of how it's being used. And you also can see that it's very different when we write something within a note versus when you have quotes from actual patients, and how that language might be. And so there's lots of challenges with representing text data and how to use text data moving forward. And these are just a series of kind of silly statements, but you can see where you run into difficulties with language. And I think we have a very easy time of separating these things out and figuring them out. But it's hard to teach computers to be able to isolate and kind of figure out what words be associated with what words, and what their kind of meaning might be within these sentences themselves. And just to highlight some of the other language difficulties you can have morphological difficulties, syntactic. There's lots of, I think, interest around negation in medical text because of its significance as far as information extraction techniques. So there's, I think the take home is it's not easy, although there's been a lot of advances over the last couple of years. And language is inherently different than kind of what we talked about in the past as far as imaging data. So imaging data, you have this kind of spatial relationship. it makes sense to kind of look at little small blocks within the image itself, and to have network architectures to kind of leverage that spatial representation to learn features. But language in itself is more in a sequence type fashion. And so you would think that, there would need to be a difference in kind of the underlying architecture to learn these types of things and how to represent that data underneath. You can still use deep neural networks in this sense, but what you really need is you need some type of kind of recurrence, something that takes into account the kind of past information that's happened within the sentence. So, when you have that next word that's coming up, you really need to know kind of what are the words that have come before it if you're trying to make a kind of a prediction of what that next word might be, or if you're trying to make a prediction about what the next sentence might be, or, if you're trying to represent the entire sentence and you need something to kind of embed, and we'll talk about that a little bit more, that sentence so that you can use it in another task. And so this is kind of a graphical kind of representation of kind of what those recurrent neural networks look like. And basically, the thing about it is that, you have this aspect that, that comes out of the neural network kind of as it's being fed data that then feeds back in for the next step. And so this is kind of the unrolled version where, this might be the first word, the X0 here. This is going to, X1 is the second word in your sentence. And at each stage, the network is not only making a prediction about kind of what its task was for that particular word, but then also feeding in additional information into the next prediction. So this is how you kind of represent sequence data within the networks themselves. And one thing I should talk about briefly, and I did mention this in the natural language processing talk, was this idea about embedding. So one of the things you'll quickly kind of notice is that when you're working with text data and you're isolating words, is that it's a pretty sparse representation of data. If you have a dictionary of 100,000 words and you have a sentence, and I want to represent like opioid as a word, it's going to basically have a vector or kind of a representation that has 100,000, well, have 999,000, etc. zeros, and you have one that's representative of the opioid word. And so you get these very, very sparse representations. And one of the major breakthroughs in the last kind of 7 to 8 years from the standpoint of NLP is this idea of kind of creating embeddings or lower representational states of those words. And based on the context and how those words are used, and so it captures things like kind of semantic relationships between words. And I won't go a lot into that at this point, but the idea is basically is that you kind of, every word is kind of, is best kind of represented by the other words that are surrounding it. And so you can learn representations of words by how, what words are surrounding them. And then you can kind of choose or kind of force those words to be represented as smaller vectors or representations of those words in space. What's nice about that is then you can then feed those embeddings into some of these larger kind of deep learning networks. And I'll give you just kind of an idea of visually what this looks like. So this is some work we did with chief complaints and embedding chief complaints. And the way these were constructed is that we took sentences that I would say kind of represented the chief complaint as kind of by the patient. So, you have 2 or 3 sentences when the patient walks in, and then we took that and then used the sentences to construct embeddings for the individual chief complaints. And you probably can't see the screen very well, so I'm going to blow up a section over here just to be able to kind of give you an idea. So this is, these embeddings we've mapped down to 2-dimensional space. Most of the embeddings are in kind of, they might have up to 128 or 256 dimensions, but we map them down to 2 dimensions and put them out graphically over those 2 dimensions. And you can see it kind of captures well a lot of kind of the semantics behind those chief complaints. Like all of the kind of urinary complaints are mapped together. You have a lot of kind of the abdominal complaints and vaginal complaints and GI problems that are all mapped together. So it gives you a pretty good idea that, it is that these types of embeddings are capturing information in the words themselves fairly well. And then for kind of downstream tasks, so you've kind of learned some of these embeddings for these words. What kind of things that can you do with that information? If you want to be able to predict, let's say, again, let's go back to kind of the sepsis example, and I want to be able to take a series of kind of documents and use those documents to make a prediction about sepsis or something like that, then you can feed the individual kind of words through their embeddings into some type of other deep learning network. These are long, short-term memory networks, and get to a particular kind of outcome prediction from that. So again, the idea is that you have some data representation, and really, I would say the data representations is kind of twofold at this point. One is that the individual word, you have some new data representation for those individual words, and then you also have a representation of the sequence of words together, and then that's used by the kind of final layer within the neural net to make some prediction coming out of it. These are incredibly effective. There's been a lot of advances over the last 3 or 4 years in this space, and a lot of the kind of issues that I highlighted as far as language difficulties, there's been a lot of progress in that space that's been made during that time. Okay, so we will change gears here and move into the deep learning for tabular data. This is probably data that you're more familiar with. This is, I think, we kind of think about this data all the time. It's the Excel data where you've got some type of variable that's represented by a column, and then you have rows that may represent patients or emergency departments or something along those lines, or visits or something from that standpoint. And for a long time, tabular data was a little bit different than imaging data and text data as far as the performance of deep learning versus some other techniques like random forest or XGBoost, if you've heard of those types of things, and that people weren't seeing huge performance differences with this type of data. And some of it has to do with the data sparsity. We kind of touched on that with language and kind of words, but you can also think about it when you have categorical data is if you have a variable with 20 categories, the only way to really feed it into one of these neural networks is to represent each categories in a kind of what we typically say is like a one-hot encoding strategy where you have a 1 for a particular value of that category. So if you have a categorical variable with 20 values, it would be represented by kind of a vector of 20 of length 20 with kind of a 1 in each spot for when it had a particular category value. And so they some recent work in this space is really taking the same approach that they did with text data and started to learn embeddings that are then used with the tabular data, and then combining those embeddings with continuous data that are then fed into the neural networks. And so it kind of looks like this. This would be like a typical architecture you would see with this, is that you have your categorical variables over here, so stuff like gender and insurance and race, and whether the patient has hypertension. You learn a particular embedding for those variables. We won't really talk about dropout today, but it's basically kind of a regularization technique. But those are learned and those are fed into kind of further downstream into the layers of the deep neural nets. And then you also take your continuous and you do some normalization with those, and you feed that in as well. And it's then the same idea as we kind of illustrated before. So you have multiple layers that are learning better feature representations or data representations, and then you make some final prediction kind of as the final output of the model itself. The last data kind of area I wanted to touch on was graph or network data. A lot of you may have not seen this type of data. There's been a lot of kind of recent work on this, and I'll kind of just explain kind of what types of data are represented by graphs and how that might be different. So typically we're used to regular type of data structures. We have images that have a very regular structure to them. We have time series data or text data where they have a particular type of sequence data to them. And you can even think about tabular data being kind of in that space. But there's a lot of other types of representations of data that are well suited to representations in graphs, such as social networks and kind of the web information. And a big area that's now kind of growing out is in knowledge graphs, where you have connections between different concepts and the relationship through graph structures and kind of deep learning networks that learn on graph structures. Just to give you two examples, so this is some work that we're currently doing with kind of opioid trajectories and looking at the kind of networks for opioids. And so these are the connections between a lot of different types of events that terminally end in an opioid event. And so that's would be one example of a particular type of graph structure. This is another example of kind of just a mock-up example from kind of the movie world. It's meant to kind of show what a knowledge graph would look like or represent. So where you have these nodes that are representing names or entities, and then you have some type of particular relationship that kind of links the nodes together. And for the kind of medical world, you can think about this, would it be like, you have links between pieces of information like, you have valvular insufficiencies, and that can be a particular cause for heart murmurs. And that information right now is not well represented within electronic health record data or anything else. And so using the knowledge that we have that's in text and other things and extracting that out and building these knowledge graphs can be particularly helpful, kind of with increasing or enhancing some of the kind of initial work that's been done with predictive task and on a lot of these areas. The kind of process itself, it's not that different. We won't go to the specifics of kind of the learning or kind of how you learn on graphs. But the basic idea is that you have kind of your graph structure. You have some type of way to map that graph structure into the neural net. It does the same thing it kind of did before, where it learns kind of a new representation of that data, and then you have some type of kind of output or outcome that you're trying to predict at the end of it. And so this is, I just wanted to give a kind of an example of some of the work that we've done in the last year in this space. This was a particular task that was looking at semantic similarity between sentences and trying to kind of arrive at a score about how similar two sentences might be on a 1 to 5 score. So you can kind of read through these sentences and kind of give your own general impression about how similar they might be. But one of the things that we did with this particular task is that we combined some NLP techniques with also using a graph-based or knowledge network on top of it, and then fed the combination of those two things into the final classifier. And so at the bottom of these, you can see how those sentences are represented within the graph and how they have very similar structures for the ones that are similar, and how they have different structures for the ones that are somewhat dissimilar. And that by introducing that kind of graph knowledge network within the task itself, it improved the overall kind of prediction or classification for this particular task that we were kind of setting out to do. And then the kind of other areas in this space is then combining all of these different techniques together. So, using tabular data and text data and image data and graph data all together for some particular task. And you could think about this from the standpoint of, let's say like predicting 30-day cardiovascular outcomes for patients that come in with chest pain. And it's entirely possible where you could combine their EKG data that they had the tabular data that they have from the electronic health record, the provider notes that they have, and then also any CT imaging or chest X-ray imaging they have, and then in addition to that, combining that with any kind of knowledge graphs that you might have or might have learned to make the kind of final prediction. And so you can see how it's a much richer kind of representation of the data itself and of the visit that you're having. And you can see how you could potentially get a lot better prediction coming out of it. The last kind of one piece or an idea I just wanted to impart was this idea behind transfer learning. So we've talked a lot about kind of how these deep learning networks kind of change or manipulate their kind of structures to better represent the data. So one of the things that you can do is you can take those representations of the data that are kind of embedded within the middle part of the neural networks, and then use those data representation on other tasks. So one example would be, I'll just use as kind of the word embedding technique. So if you had a large corpus, and this is what happens kind of in the real world, is you have some corpus like Wikipedia, and basically the more data that you have, and the more text that you have, the better kind of representation of the embedding for a particular word, because you get to see or learn how that word is used in a variety of contexts. You can then take that embedding or that learned kind of representation of the word and then use it in a different task. You could easily import that kind of information or transfer that information into the task that you're using in kind of the medical space. It's entirely possible to kind of learn other representations within the medical space. If you're in a large institution and you have access to a large amount of data, and then take that information and move it or transfer it into other areas. And what you're not transferring necessarily individual patient information, you're transferring kind of learned representations of how that data is interacting and kind of the kind of space that it sits in kind of overall for a particular objective task. It's saying my internet is unstable, so hopefully you all can still hear me okay. It's fine. And so I just wanted to kind of leave with some practical recommendations. So I think if you're doing some type of research that's involving imaging data, or it's involving text data, or it's involving something with graphs, I think at this point, kind of in the research world, you really need to be using deep learning methods for those types of things. From a performance standpoint, kind of from a prediction, from an understanding standpoint, all of those things I think are enhanced through using deep learning. For tabular data, which is kind of a lot of what we used to working with, I still think it's possible to get pretty good performance using XGBoost or random forest or other things. But I think increasingly, as people start leveraging multimodal data, I think that it will be more and more often that deep learning is used for these particular tasks. Some other things, obviously there are particular areas of expertise, and I would say even for each of these individual kind of data areas, there are people that have expertise in deep learning for images versus text versus graphs. So a lot of times it's going to take a multidisciplinary team to kind of carry out one of these tasks. And then the other thing that I would kind of caution about is just understanding the compute resources and limitations. So a lot of these deep learning networks require significant computer resources, lots of graphic processing units. You can either use that from cloud-based computing, or if your institution has some type of kind of large computing resource, that would be kind of ideal. But a lot of times these are not going to be able to be done on your laptop or even a desktop computer. And then, what are some of the current drawbacks? So right now, I think one of the major drawbacks from a practical standpoint and use and actually changing patient care is that there are still a lot of implementation difficulties. It's one thing to kind of get this data out and have it stored and use it, and make some prediction. But moving that prediction kind of pipeline into some type of real-time environment where it can actually make a difference, I think it's difficult currently in a lot of institutions. And so it may be that you learn a lot of interesting things from these things, but you may ultimately have to fall back on some much more simple architecture, or have some of the aspects of things stored through deep learning. So some types of data representation stored in deep learning, and then utilize that data in real time with some type of more simple architecture. So again, personnel is an issue. If you're in an institution that doesn't have a lot of people that are doing this, it's obviously something that would be a drawback. And the last thing, I think, I didn't talk a lot about kind of the black box nature of this. Hopefully I've opened up that black box a little bit, but there are advances in this kind of space of being able to lend deep learning to interpretable methods. So you saw with the pneumonia and chest x-ray kind of how the network is identifying areas, and that's increasingly becoming common in a lot of different spaces. There's definitely the recognition that these models need to be interpretable to be used well within kind of both the clinical domains and other spaces. But that's ongoing, and I would just say that some are still very, very difficult to interpret exactly what's going on underneath the hood. If you're interested in kind of getting involved and doing this type of stuff, I would say, 10 years ago, it was very difficult. You really needed to have like a very, very solid computer background and also math background. But increasingly, there are platforms out there that allow fairly easy coding and of these different neural networks. And I've just listed some here to look into. But it's not too difficult now to kind of get up and running with some of these, particularly if you have some kind of computer science or math background behind it. So I will stop there. I can open it up for questions. If you have any questions, please let me know. But thanks very much for allowing me to speak today. Thank you, Dr. I'm going to stop my screen share just real quick.
At this time, we're going to open it up for discussion. If anyone has any questions, feel free to unmute yourself and ask your question, or you can type it in the chat box at the bottom of your screen. All right, we're just going to give it a couple more seconds, Dr. Taylor.
That's okay. And if you have any questions, feel like you want to ask them here, that feel free to email me as well. I'm happy to talk.
All right, I guess there are no questions. Well, thank you again, Dr. Taylor, for this great presentation. Thank you to everyone watching, and I hope everyone has a safe and healthy rest of the week.
Yeah, thanks everyone.